All right, this is going to be lecture 6, Encryption, Decryption, part 4. Okay? All right, we start with these guys. Ralph Merkle and Marty Hellman came up with this knapsack thing where you come up with a combination of values to fit in there to make a target sum, what we just talked about. Easy enough there. Again, here's how it works. You pick a simple super increasing knapsack. Remember, that's where each number is greater than the sum of all the prior numbers. Then we take that number and calculate a hard knapsack. Then we encrypt our message. That's all there is to it. This is a bunch of steps, but they're all easy steps. Okay? All right, so a receiver. So me and Austin here are going to talk. So Austin's going to be receiver. He would pick a simple super increasing knapsack. He would also pick a multiplier and a modulus. Okay? We talked about modulus in this class yet? Okay. Modulus is remainder. We're going to see plenty of examples of it today. We're going to learn about remainders. You all remember 4th grade math where you put the numbers and you had the divisor symbol over it and you did the 2 goes into 5 2 times with a remainder of 1. So the remainder would be 1. The modulus would be 1. Okay? We're going to do that. Okay, so we pick a simple super increasing knapsack, a modulus, and a multiplier, which I will supply to you, by the way. I'm going to give you all that to you. So here we picked 1, 2, and 6 as our simple super increasing knapsack. First thing we do is check it. Is 2 bigger than 1? Obviously. Is 6 bigger than 2 plus 1? Yeah. Obviously. Okay. But again, we're working with teeny tiny little baby numbers here. If we had, 200-digit numbers, this would be a little bit harder to do. Okay? Plus, this can be automated anyway. Then we have our multiplier, which is 11, and our modulus, which is n. N should be prime. But I will tell you now, for the sake of some of these exercises and samples, it's not always prime. Because I have to somehow make the numbers do different things, and you just go with whatever I tell you. Unless I'm asking you the question, is this super increasing? Well, then you tell me if it is or isn't. But don't just say, oh, can't do it, and it's not prime. Well, just use the number I'm giving you. Okay? All right, so we compute a hard knapsack. So since we have three elements to our simple knapsack, we would end up with 3 to our hard. I'm going to show you how to do that. So h to the I is equal to w times s to the I mod n. What that means is h1, in which the first digit of our hard knapsack, is equal to w times the first digit of our simple knapsack mod n. Okay? So h1 is equal to w times s1 mod n. So w is 11. We got that from right up in here. We got 1. So remember, s1 is 1. So this is our w. S1 is 1, and this is our n. So 11 times 1 is what? It's tough. 11 times 1 is 11. So then 11 mod 13. Here's the way you do modulus. This is important. You know how to do this. You take the 13, and I'm going to draw on this slide real quick. If I can find the little draw thingy-hoozy. Come on. Where's the draw thingy? There it is. Okay. I want red. So if I put 11 right here, then I'm going to put this thing over it. Y'all remember that? Okay, from 4th grade math? About 4th grade, wasn't it? I don't know. Then I would take the 13, and that goes in front. So the 13 goes here. You're going to want to do it differently, trust me. Depending on the size of the numbers, you're going to want to do it the other way. But remember, the second number always goes in front of the division or the divisor. So 11 goes underneath the little house. 13 goes in the front. How many times does 13 go into 11? I'm thinking that's up here we're going to write 0. Then we're going to write remainder of what? 11. Y'all remember that? Remember those days? Remember, 13 didn't go into 11. So we're not going to do the point whatever. We're not going to go into decimals here. Just doing basic division. 13 does not go into 11. So we have 11 left over. So the answer is 11. Easy enough. So the second one, or S2, our second digit of our simple knapsack is 2. So now we take W, which is 11. So 11 times 2 is 22. Mod N, which is 13. 22 mod 13. Again, 22 goes underneath. 13 goes in front. We put our little house over it. 13 goes into 22 once. Okay? And we have 9 left over. So the modulus is 9. Everybody see that? Very, very basic math. So remember, 13 goes in front of 22. 13 goes into 22 once. We have a remainder of 9. Modulus 9. That's it. Modulus is nothing more than the remainder. Okay? Our third digit of our simple knapsack is 6. So 11 times 6 is 66. 13 goes into 66 a few times. The remainder is 1. Okay? It's like 5, I think, isn't it? Yeah, 5. So 5 times, remainder of 1. So the answer, our hardened knapsack is now 11, 9, and 1. Easy enough? So far, so good? Okay. So we went from 1, 2, and 6 using 11 and 13 into 11, 9, and 1. Okay.
It's not super increasing anymore.
Correct. It only has to be super increasing on the simple knapsack.
Okay.
Hard knapsack, no. You stop doing that. That's a very good question. You know, no one's ever asked that. Ever. It's good.
I feel special.
Yeah, you feel
That's
nice.
extra credit, right?
Either special or not so. No, just kidding. No. Yes. Did I do any extra credit in this class yet? Yes, I did. I did extra credit.
Yeah.
Okay.
I did it, but
I don't remember who did it, who got it. Somebody got
It
it.
was an encrypted thing on.
It was like the shift was 13, I think. And I think I even put the answer up there. Didn't I put the answer up there?
No, that wasn't encrypted. You asked me who you encrypted who was the father of something.
Oh, that's right. Okay, but I put where I did it with. I encrypted with 13. And the answer who the father of was what? What's his name? Was that Claude Shannon? Yes. Okay. All right, so let's continue on from there. All stuff I give you like that, you might see again somewhere. I'm just saying. Okay. You wrote a good book, too. Might be a good idea to know the name of that book. All right, now, it's actually in your slides. We've already covered it. Know that slide. So, the receiver sends, so I send the 11, the 9, and the 1 to Austin. Okay? He, I keep the simple, the W, and the N. Okay? I don't share them with anybody. Okay? Now we want to send this plain text. Again, plain text is always in binary. You want to send 101, 010, and 011. They're broken into groups which happen to be equal to the number of digits in our hard knapsack. That's why they're in groups of 3. Okay? So, we go 11, 9, and 1, and we put 101 above it. So 11 times 1 plus 9 times 0 plus 1 times 1 gives us 12. Then we use 11, 9, and 1 again. Now we're encrypting 010. So it's 11 times 0 plus 9 times 1 plus 1 times 0, and we end up with 9. And then 011 is 11 times 0 plus 9 times 1 plus 1 times 1 gives us 10. So our ciphertext is 12, 9, and 10. That would be the stuff we send across the internet. That's the encrypted message. Okay? So far, so good? Easy enough. That's all there is to encrypting it. Good to go? Decrypting it's a little bit tougher. Not a lot, just a little bit. Has anyone looked ahead and watched all these already? Oh,
I don't know if I count.
All right, so 13 modulus 8. This is just a sample of modulus again. I'm not 13, 33. Take 33, that goes under the house. 8 goes in the front, okay? So, it goes in 4 times, okay? So 8 times 4 is 32. Modulus of 1, exactly. Okay? But if we just divided it, we end up with 4.125. So that's one way you can calculate it. We can just divide it, then take the whole number times the 8, and then subtract and get the difference. So that's one way you can do it. Because your calculator, actually, yeah, our calculator, actually, hold on. Calculator, where are you? Okay, there we are. Yeah, these will do it. If we go to, is it scientific does it? Yeah. So if I did 33 modulus 8, 1. There you go. Does it for us. Not all calculators do that.
Just Google.
Yeah, Google will do it for you too. Okay, everybody okay on modulus? Yes, you will be doing this some again. Now, there's 3 different ways of calculating what's called the multiplicative inverse. Okay, you need to know all 3 ways. I'm making you do assignments using all 3 ways. Okay. All right. One way is by using w to the n minus 2 mod n. Okay. So if n is 13, w is 11. So, and this is not w raised to the minus 1. It is not. It's called the multiplicative inverse of w. Okay? Multiplicative inverse of a number. So, the multiplicative inverse of a number is equal to w to the n minus 2 mod n. So we just plug them in. W is 11. N is 13. So 11 raised to the 13 minus 2 mod 13. So 11 to the 11 mod 13. Easy enough? You can do it on a calculator. It comes out to 2853116700611 mod 13. And the remainder of that is 6. That's one way. You can use your calculators. Actually, there's a very easy way to do it by hand, and I'm covering that next lecture. Because when I originally did this, I made them do it all by hand. But an online class requiring me, making you do it by hand? I'm sorry, how many of you would actually do it by hand?
Definitely, maybe.
Few. You'll probably do a couple of them.
I might try the first time.
Right.
And say bye-bye.
Because it's actually very simple to do, and I'll show you that next time. Okay. Here's another way, method number 2. This is the comparison method. You need to know how to, because we will actually be using this again with another encryption routine. It's very simple. Okay, again we use n and w. So what we do is we put n down here, okay, and w. So we put down n, w in comparison. And we put a 1, 0, 0. That's just what you put there. So n is 13, w is 11. We put 1 under n, 0 under w, and 0 under comparisons. Then we start. From that point, we go down. So we do n plus 1. So 13 plus 1 is 14. W plus 0 is 11. And obviously that was the first comparison. Okay. Then what we're doing is we're looking for matching numbers. Do 11 and 14 match? Does 11 match 1? Does 11 match anything? That's what you need to be asking yourself. So we add it again. So 14 plus 13 is 27. 11 plus 11 is 22. This is our second comparison. Does 22 match anything up here? Because we've only done up here so far. We've done these 3. 22 does not match. So we add it again. So 27 plus 13 gives us 40. 22 plus 11 gives us 33. Again, 33 doesn't match anything up here. So 40 plus 13 gives us 53. 33 plus 11 gives us 44. Again, 44 doesn't match anything up here. Then 53 plus 13 gives us 66. And obviously, we get 66 down here. Okay? So, 33, 44, 55, then 66. You always go by the area where W matches. And you'll notice that this W matched on the 6th comparison. You see that? Don't go by where it matches with N, because that would be the 5th comparison, the 5th line. But really, where W matches is what you go with. And 66 matches on the 6th time, basically.
It's really easy to do with Excel.
Yes, it is. Very, very simple to do with Excel. How do you think I make all your assignments? I do it in Excel. It's so easy. Okay? So remember, you put N and W, then you put 1, 0, 0. Then you just keep adding them up. Don't let stupid math errors throw you up. Now, what if W was 1? Okay? Just pretend it was. So if W was 1, what would the answer be? If N was 13 and W was 1. Anyone know what the answer would be? So, if W was just a 1, if this was just a 1, so this would be just a 1, this would be a 2, this would be a 3, so on and so forth. Follow me? It'd be 1 because this 1 matches with that 1. So the answer would be 1. That's very important because you're going to see that on your homework. So many people miss that. They don't realize you can actually match with that first number. Everybody see that? Okay. Just watch that. Okay, let's continue. Method 3. I like these nice colorful slides. Aren't they pretty? They like show where everything comes from. So again, we have n, and now this is exactly where you're going to see it, by the way, on the test. Okay, this is the w to the w way of doing it. So 11 to the 11 mod 13. Now, if you'll notice 2 slides ago, this was w to the n minus 2, which still turned into 11 to the 11th. Y'all notice that? That doesn't mean it's the same thing as here. It just happens to be the numbers in this case were the same. But so remember, we had w to the n minus 2 mod n is one way. Then we had the comparison way. Then this way is w to the w mod n. 3 different ways of doing it. Okay? So w to w, 11 to the 11, turned out to that huge number we saw before. Again, it ends up with 6. So all 3 ways. Now, for your assignment on this, they won't always turn up with the same result. Do not do one of them, then assume the other 2 are all the same. They don't always work out. The one that's closest to the way it would work in real life is the comparison. I just want you to know the different ways because you'll be using the other ones again later on. Okay? It was funny because Grant Cadis, some of you know the name Grant before. He went to TU. He came up with a way of doing this. I don't remember how he did it, but he came up with this great way of doing it. It was flawless as long as you use a specific number to encrypt. Encrypt anything else, it failed. Because he's like, this works perfectly. I tested it over. Yeah, he tested it with one number. It went great without one number. Doing anything else, it failed miserably. He's like, oh, that sucks. So it was just funny. Gave him such a hard time. Okay. So, if you remember from the prior slides, our ciphertext ended up being our hard knapsack times our plain text. And I'm going to show you what that was. That was right there. Remember, our hard knapsack was 11 times 9 and 1. Our plain text was 1, 0, and 1. So that's where hard knapsack times P came from. Hard knapsack was actually W times the simple knapsack times P. It's not critical you know this information right here. We're just showing you that this top stuff, these first 4 bullets, not all that important. It's just showing you some math behind it, okay? But remember a minute ago, we just got done calculating, suck at drawing circles. That's a circle. Remember, inverse of W is a 6. Y'all remember that? And our ciphertext is 12, 9, and 10. Okay. So, we got our 6. Now, to decrypt a message, we use this. The inverse of W times the ciphertext mod n. Okay? So, to decrypt a message, we use the inverse of W times our ciphertext mod n. That's our plain text. Now, so the inverse of W, where'd my mouse go? Lost my mouse. Where's my mouse? Oh, it's up there. So the inverse of W is 6. Remember, our first ciphertext is 12. So 6 times 12 is 72. Mod n, which is 13. Again, we put 13 in front of 72. We get a remainder of 7. 7 is not the answer. But 7 will be the answer on a test. But it's the wrong answer. Because now you have to convert it back to binary. Because remember, we're encrypting a binary message. Remember that? So how do we get 7 into 101? Now what we do is we take this 7, and what combination of our simple super increasing knapsack will give us a 7? 101. Y'all see that? 1 times 1 plus 2 times 0 plus 6 times 1 gives us 7. So the second one, 6 times 9, 9 is our second ciphertext, gives us 54. Mod 13 gives us 2. So what combination of 1, 2, and 6 will give us 2? Well, obviously just 2. So 0, 1, 0. So far, so good? I know some of you are like, what in the hell is he talking about? Okay. 6, 10. 10's our third digit in our cipher. Oops. Our third. ciphertext number. 6 times 10 is 60. Mod 13, again we put the 13 in the front. The remainder ends up being 8. And what combination of 1, 2, and 6 gives us 8? Well, obviously it'd be 2 and 6, so it's 0, 1, 1. Everybody see that? Yes? I mean, it's not hard. It's just a bunch of steps. And I will tell you, you're going to stop at the 7, 2, and 8. You're going to be like, I'm done. No, you're not. You're so close, though, but it's still wrong. Okay? All right. Here's an example, exactly like you will see it on the test. Exactly. Numbers probably change, but format will be the same. Okay. Given this simple knapsack, first thing you do is check to make sure it's super increasing. Multiplier W modulus N. Compute the hard knapsack. Remember, it's H to the I is equal to S to the I times W mod N. So it's 1, which is our first digit, times 11 mod 13. Then it's 3 times 11 mod 13 and 6 times 11 mod 13. Y'all see where that came from, the yellow. Okay. Then we end up getting 11 mod 13 and 33 mod 13 and 66 mod 13. Are we okay with that? Remember, 13 gets run into 11. Doesn't meet. But I tell you, I've done it. So many people do. You're going to look at 11 mod 13. You can say the answer is 2. It's just, I think it's our brains. We just see that number and we're like, oh, 11 is in 13. One time got remainder of 2. That's wrong. It's the 13 has to go in the front. I mean, when the first digit's bigger, it's not an issue. Students get it right perfectly every time. But when the first digit's smaller, it screws with our brains and we have to go the other way. See what I'm talking about, everybody?
How many people give you a test on that?
Not many. Yeah, so just remember, the right part goes in the front, then you divide. Don't give me a 2, because it's going to be wrong. Okay. All right, then I say encrypt the number. Remember, we got the hard knapsack there. Now we encrypt it using our hard knapsack 11, 7, and 1. We get our ciphertext, so the answer there would be 12, 7, and 8. Okay. And there is a practice assignment. I hope you're all doing the practice assignment. It's going to be very critical when you get to AES. Because if you don't understand the practice, you're going to so screw up the assignment. Okay. Then we decrypt. Okay. And when I tell you to do these, I'll either tell you which way to do it or they will all work. Okay? If I don't tell you, use the comparison method. Any way will work for this. But sometimes they'll tell you using the W to the W mod N or using the W to the N minus 2. So if I don't tell you, they will all work. Okay? So you should be able to follow the numbers there. I had some students that went from here to University of Tulsa, and this was the set of slides they wanted me to send them. Because it's all color-coded and nicely broken out, and they can follow the numbers, and it is. I mean, that was a lot of work to draw that. But, everybody okay on what to do here? Not hard. But, you know, don't give me the intermediary value, okay? Yeah, in this case, don't give me the 10 and the 4. That's like halfway there. Well, it's like 3/4, but it's close. Because remember, 10 and 4 are the intermediate values, and you have to figure out what combination of the 1, 3, and 6 gives us 10. That'll be 1, 1, 1. And what combination of 1, 3, and 6 gives us 4? That'll be 1, 1, 0. Easy enough? Okay there? All right. Now, a little bit more information about this. The modulus is approximately 200 bits long. So that modulus, we're working with a 13. Imagine one that's 200 bits long. The simple knapsack digits are 2 to the 200th digit apart. So if the first one's 1, the second one is a big old number. Then the third one's even bigger than that. And the knapsack actually is made up of 200 terms. We're working with, what, 3 over here? Imagine working with 200 of them. Okay? So each term ends up being between 2 and 400 bits long. So very, very large numbers. It would take 10 to the 47th year to try 200 digits. or to try to the 200 choices. That's a lot of years. Okay? And it's hard to break for very large values of m and n. Okay. Hasn't been broken, by the way. Not really broken, but you'll read about it in the book. But it says, if modulus is known, it is possible to determine the simple knapsack used in polynomial yield time. In other words, it's not hard, it just might take me forever, because there's so many digits. Okay? And they proved it. So, all right, here's exactly the way you're going to see it. I'm going to tell you to compute the hard knapsack. I'm going to tell you to encrypt this number, compute the inverse of W, and then decrypt a number. It's exactly the way you're going to see it. Okay? Just like the samples we showed you. All right, that's the end of that slide. Discard my notations, and I want to stop.